and welcome to day 14 of the 24-day physics question extravaganza. And today we are on particle physics. So yesterday we did specific charge. So this is again another particle physics, but actually looking at decay types, etc. Okay, so we've got here an isotope of potassium, 1419, is used to date rocks. This isotope decays into an isotope of argon, mainly by electron capture. This decay process is dictated by this equation here. Okay, so what happens here? An electron comes into here, and you make argon here. So it's all about adding on each side. So to conserve, what we're going to do, we're going to look at here. So what's going to happen here? These numbers, of course, are going to be 40 and 19 minus 1, so it's going to be 18. And to conserve lepton number, given the fact that this is a lepton on this side, I must emit a neutrino, and specifically an electron neutrino here with no charge. So this question was a bit interesting. So electron capture is one of those things that you need to know. Basically, it's a neutron, it's a proton plus an electron becoming a neutron plus a neutrino, okay? So it's one of those formulas you need to know, but what they've done here is they've shown it in a slightly different way by actually using the elements to do that, okay? So this neutrino has to be emitted because it's conserving lepton number, but you could do this number here literally by adding the sides up. Okay, so there was 1 mark available for getting the numbers right and 1 mark for remembering there was a neutrino there. So explain which fundamental interaction is responsible. So it is the weak interaction because, again, explaining, must say because there are, there are hadrons and leptons involved in the interaction. Okay, so because they are hadrons and leptons, it is the weak interaction. If it was strong interaction, it would have just hadrons, because hadrons experience the strong force. Okay, so because there are hadrons and leptons, it is the weak interaction. So there was 1 mark for mentioning, actually telling me which one it is, which is weak, and 1 mark for the explanation. Okay. One decay mechanism of this krypton is that it results in the argon, or potassium, going into argon, is having an excess energy of 1.46 mega electron volts. It loses this energy by emitting a single gamma photon. Calculate the energy of the photon release. So I've got energy, and I've got an energy, and it's in mega electron volts. The first thing you need to do is convert into joules. So to go from mega electron volts to joules, you need to times it by 1.6 times 10 to the minus 19. So I've got 1.46 times 10 to the 6 times by 1.6 times 10 to the minus 19. And that equals, so 1.46 times 10 to the 6 times by 1.6 times 10 to the minus 19. I get an answer of 2.336 times 10 to the minus 13 joules. And of course, I'm after the wavelength. So I'm going to go use energy equals hc over lambda. So it's of a photon, and that's the energy of a photon. So lambda equals hc over the energy. So that's going to be 6.63 times 10 to the minus 34 times by 3 times 10 to the 8 all over my 2.336 times 10 to the minus 13. So I've got 6.63 times 10 to the minus 34 times by 3 times 10 to the 8 divided by that answer, and I get an answer of a wavelength of 8.51 times 10 to the minus 13 meters, which is about right. That is about a gamma wave there. I'm going to just check the answers here. Here we go, 8.51 times 10 to the minus 13. So I got hints from that. Calculate means using an equation, and photon implies I'm using the energy of the photon formula. So the potassium isotope can decay by a second decay process to form this calcium nuclide. Suggest how the emissions from the nucleus of a decay method can be used to confirm which decay process is going on. So I'm going from potassium, what was it, 4019, and I was going to calcium 4020. So what's happening here is that my nucleon number is not changing, but my proton number is, or my atomic number here. So this must mean that I'm having a nucleon changing to another nucleon, but what's happening here, something specifically is changing to a proton. So it must be a neutron changing to a proton, which of course is beta decay. Okay, so suggest how the emissions of it can be used to confirm which decay process is occurring. So in this case, it is the decay is beta decay. Okay, and I'm going to suggest how the emissions can confirm. So I want to have a way of confirming that it is beta decay. So there are numerous ways that you can confirm beta decay. You can have the emissions travel in a magnetic field, and it should turn towards the direction a negative charge would, because it is a beta decay. Or you could, of course, beta is stopped by a few millimeters of aluminium. So using that way of doing this to confirm it is not alpha or gamma, use paper to stop. If not, it is beta or gamma, then use a few millimeters of aluminium. If it stops, it is beta. So what I'm doing here is that I'm suggesting, just giving reasons and suggesting how we could test this was beta decay. So I've actually mentioned confirm which decay process is happening. So I'm telling you which one is happening. Okay, the decay is beta decay. And I've written the equation up here to prove it to myself. And I'm mentioning suggest ways that we can actually confirm this. We can put this in a magnetic field. And of course, due to Fleming's left-hand rule, it will orientate its way a certain way. Or of course, you can use thickness as material. So if I actually go to the mark scheme here, it's worth 3 marks. You identify it as beta emission. Okay. What you can do, any 2 from here, correct details of how an electron is detected. So that's the way I'm doing it. And I've mentioned the electron release and the antineutrino released. And by actually writing the formula, I'm actually showing that there. So if they're asking you which decay process is happening, writing the formula can actually be a really useful way of proving not only to yourself, but to the examiner that you understand what's going on. And there we have it. There's day 14, just a very simple 10-mark particle physics question.